Okay, so this video is for anyone that was not here today in class, or just for anyone that wants a little refresher of what the heck we did. So first task we did was just in their seat groups. I had students look at this particular solution and try and help me find my errors. So basically I had done this question, and it didn't work. I checked the answer in the back. It was not correct. So if you weren't here today, maybe pause. Try and identify as many errors as you see here, and then unpause, and I'm going to explain. Oops, let me go backwards. All right, so to identify these errors, students first notice that I have a power of 4 here. We haven't done anything with a power of 4 in class, so I think they probably thought something weird was going on there. They realized that what I did was I added these two exponents together to get a 4, and they reminded me that when I'm collecting like terms, the exponents do not change. And they said that was because if we imagine m was equal to 2, then m squared would be worth 4, and m to the power of 4 would be worth 16. And so here I have 3 groups of 4, 9 groups of 4, means I have 12 groups of 4. So this must be 12 groups of 4, which is m squared. So I can't be just changing exponents willy-nilly. If I am collecting like terms and adding and subtracting, I need to keep the exponent the exact same. The other thing they noticed was when I was rearranging my terms, I did not take the sign with the term. This entire piece right there is the term. When I move it around, the sign, that minus, that subtract, that negative, whatever the heck you want to call it, must go with it. So this should have been a subtract. And that happened in a couple other places too. This 4m is technically a positive, should be a positive there. Okay, did that happen anywhere else? No. Okay, so then the last thing that they noticed was I got minus 11 there from here. So what I did was I thought about it like negative 7 plus 4, which would be true if there were brackets there, but there aren't brackets there. So what I should really be doing is thinking about 0, go down 7, up 4, so I end up at minus 3. Okay, so those were a bunch of errors that they found in my solution to help me out. All right, next, we did our skills check. You guys will do that on Monday. We looked at these two strings of just tiles, and we determined the expressions to represent the weight. People identified this must be a weight scale. If you go fishing, you've maybe seen something like that before. And so they came up with expressions to represent that. They also came up with let statements to explain what their variables are, which I loved because I didn't even ask for it, but we need them. Okay, so I was going to point that out afterwards, but I didn't have to because they were awesome. So let's say we're using G and B to represent the colors. So I am going to say let B represent. And I'm not just going to say blue, though, because I have to say what the numerical thing is that it is actually measuring. So let B represent the weight. And again, your peers did this. They said that, and it made me so happy. So the weight of the blue diamond. Or better yet, the weight of one blue diamond. Because it's not all the blue diamonds, it's just one. Okay? And then they also said let G represent the weight. Again, that's the numerical piece. It's not just G for green. G represents the weight of one green square. Okay, now some people used D and S. I personally don't really like using S because I mix it up for my 5s all the time. So I picked G there. Okay, some people just use the symbols. And so they just said let this represent the weight of one blue diamond. Let that represent the weight. Love it. You'll see that's kind of what I do on the next piece as well to kind of look at it visually. So then we looked at this very quick little video. Basically, I've tied these two strings together and they teeter a little bit, and then all of a sudden they balance out. So we said, what does that mean that they're balanced? People said that must mean that they are the same weight. I was like, great. Can we write an equation now? Can we equate those two expressions that you would come up with? So, yep, they went through and they did an equation. Then I said, can you use that equation to figure out a relationship between the blue diamonds and the green squares? And the first relationship people come up with is that the blue diamond must weigh more, so must be greater than the green square. I said, all right, can we quantify that a little bit? Like, how much more? So then somebody was able to tell me that 2 blue diamonds must be equivalent to 4 green squares. I was like, oh, okay, that's great. Can we go even farther than that? And then we came up with 1 blue diamond must be equal to 2 green squares. And some people said, okay, well, if the green square's weighs 2, then the blue diamond must be weighing 4. If the green square weighs 5, then the blue diamond must weigh 10. Right? And they were subbing in and giving me some possible solutions. There's an infinite number of solutions that could work for this, but we do know is this relationship will always be true. Okay, so then I said, let's look at how we can show our steps mathematically so that other people can kind of follow along where the heck this came from. So that's what I'm going to show you on the next slide, the algebraic method. So we got everyone to sit down, we went through this together. So I first set up left side of the string is equal to the right string. That's what's on the left side, that's what's on the right side. We combined all of the add blue diamonds together to be a multiply. Multiplying is repetitive addition. And then we put the rest of the pieces out in a similar manner. And so we get this equation. This was the equation most people had on their boards. Again, they might not have drawn the symbols. They might have used letters B and G or D and S. It's fine. But then I wanted to figure out how do we go from here to then get that 2 diamonds was the same as 4 squares. And people said we can start thinking about like canceling things out. And I was like, well, what does canceling mean in terms of tiles? So we decided that we were taking them away. If I take away 2 blue diamonds on both strings, the weights are still going to be the same. They're going to be lighter, but they're going to be balanced. They're going to be equal to each other. Each one will be lighter by the same amount. So we said, all right, what does that mean if we take 2 away? So if we take 2 away from the left string, it's a little lighter right now because I haven't taken it away on the other string, but what I'm left with is 2 blue diamonds and that 1 green square. Rebalance it by taking 2 away from this side as well, and we have no more blue diamonds, and we have 5 green squares. Okay, great. I don't really need to write that 0 times something because that's just 0, so clean that up a little bit. And then can we go any further? Yep, everybody said we can get rid of 1 square from both sides. So I show that algebraically by subtracting a square, and then I physically do it in my diagram, and I'm left with 2 diamonds, no squares, and on the other string I'm left with 4 squares. Okay, again, I can tidy up. I don't really need that 0 times something. So that's that first relationship that students noticed. Then we wanted to go one step farther, right? They were able to tell me 1 blue diamond was equal to 2 squares. What's happening there is we're actually splitting this into 2 groups. So I'm not removing things, but I'm splitting them into groups. Splitting into groups is division. So when we divide into 2 groups, we end up seeing that we get 1 blue diamond and 2 green squares. So that relationship. Again, I can't actually solve this fully. I can just find the relationship. If I told you one of the values, you could find the other one. But without me telling you, you can't actually finish this off. Like, that is finished, I guess, is a better way of saying it. Okay, so then I put them back on the boards, and I put up these 6 questions, or 5 questions, because that last one was question 1. And they worked on coming up with equations and simplifying them and seeing what relationships they could build. So I'm going to go through a couple more of these as examples. I'm going to skip over question 2 because it's very similar to what we just did. It's actually a little bit different than the one the students did on the board today. I'm going to go right to number 3, because number 3 now we don't have shapes, we've got some letters, so it's introducing us a little bit more to that algebraic model. Okay, so I'm going to just set it up again. It's balanced, right? This is horizontal, so that means the weight must be the same. So we have the left side weight must be equal to the right side weight. On the left side, we've got x plus x plus x plus x. We've got 4 x's. And we've got 2 y's. On the right side, we've got 1, 2 x's. And 1, 2, 3 y's. So that means the left side weight is 4 times the weight of one of the x's, plus 2 times the weight of one of the y's. Similarly, the right string, 2 times the weight of an x, 3 times the weight of a y. To simplify this, to make my strings a little bit lighter, but still balanced, I can get rid of one set of x's, one on each side, and I can do that twice. So I can subtract 2 x's from both sides. I'm going to write it directly below its like term. X's are like with x's. I am left with, I had 4, I got rid of 2. I am left with 2 x's. This guy and this one. I am also still left with the 2y because I haven't done anything to that. It's still there. On the other side, I had 2. I got rid of 2. There are no more x's. Those are all y's. So I'm 0x. I don't really need to write that down. I still have my 3 y's though. Okay, what else can I get rid of? Well, I can also get rid of a y on both sides and another y on both sides. So I can get rid of 2y on both sides. Again, if I do it to both sides, I'm still balanced. What am I left with on this side? Well, I still have my 2 x's here and here. But I've got no more y's. But that weight is still equal to the other side, and on the other side I have 1 more y. 3 minus 2 gives me 1. Okay? I don't actually need to write that 1 though. I can just write y. 1 times anything is just whatever that anything number is. Okay? That's the final relationship here. I don't need to worry about splitting things into groups because this is already just one group of a y. So that means this y must be the same weight as 2 of those x's. So if I told you, if x weighed 6 pounds, then y must be 2 times 6. Y must be 12 pounds. Or if I said x was equal to 3 pounds, then y would have had to be 2 times 3, 6 pounds. Right? So we could keep going there if I had the rest of this info. But if I wasn't given this, then I don't know that. This is it. This is the relationship. Okay, let's do one more. Actually, let's go right to this one. Okay, just so that I can show you a couple of examples without this video being a little bit long. So here, I don't have a mobile anymore, I just have the equation. It's still equal though, I still have one expression equal to another expression. So it's the same idea. First thing I'm going to look at, are there like terms here? Yes, there are like terms. I can put those together. Okay, do that first. Notice that I only looked at like terms if they were on the same side. Like I didn't put this with this because there's an equal sign. They're on different strings. If we think about it back to the mobile. But now I've simplified both sides of the mobile. Start to think, what can I get rid of from both sides? I can take away 5 of these x's from both sides. What am I left with? Well, if I took away 5 x's here, it's gone. No more x's. That's good. That was the whole point. That means the left side, all I'm left with is a weight worth 15. On the right string, I have a weight of 8, and I still have 4 x's left. 9 minus 5 gives me 4. Okay, so that means on this left side, if I think about it as mobile, on this left string, I just have weight of 15. On this side, this is equal to a weight of 15, but I've got 8 individual weights, and I have 4 unknowns. I want to know what the 4 unknowns are worth. And then I want to know what each one of those unknowns are worth. So I got to get rid of this 8. So I'm going to take away 8 from both sides. Keep it balanced. Keep it weighing the same. 15 minus 8, 7 now. So we're getting, again, lighter and lighter strings, but still equivalent. 8 minus 8 is 0, and we're left with 4 unknowns. So now what this basically is telling me is that I have 4 boxes, and those 4 boxes in total are worth 7. But I want to know how much are in each one of those boxes. Okay, it's not 7 in each one. I'm breaking up that 7. So if I'm going to break up a 7 to put it in 4 boxes, what I'm actually doing is splitting it up into 4 groups. When I split it up into 4 groups, that's going to tell me how much of this went into this one box. Okay, decimal-wise, 7 divided into 4 would get me 1.75. But again, in grade 9, we actually love fractions. Sounds weird because I know not all of you love fractions as much as I love fractions, but you'll learn to love them. Maybe not, but we'll all get to using them. The reason we leave it as a fraction is because let's say this was 7 being split into like a really weird number like 31. If I punch that in my calculator and divide it, I'm going to get like decimal and then just some weird thing that just kind of keeps going, and I have to round. I don't want to round. I want an exact answer. 7 over 31 would be an exact answer. Okay, so that's why we like fractions. So that was our lesson for today. We will spend another day next week on solving equations, but I would like you all to try some of the practice work this weekend and see where you get so that we can kind of start with a basis next week for everybody. Okay, other than that, have a great weekend.